thanks for the introduction. So while I'm still on the title page, let me say a little bit about what this talk's going to be about. So we've got two different types of things, inversion hyperplane arrangements and Schubert varieties. So these are geometric objects. They both come from algebraic geometry. Of course, one object there, Schubert varieties, we already heard about. They're pretty complicated geometric objects. The others are not. But they both have very combinatorial aspects. So what I'm going to talk about is a connection between these two things, and mainly focusing on kind of features that appear in the combinatorics of these two geometric objects. So let me set the scene. So throughout the talk, we're going to have W be a finite Weyl group of rank n. Such an object has a root system. The root system splits into positive and negative roots. Positive roots correspond to reflections, and if we take the reflections, so these roots are just vectors, we look at the orthogonal complement to those vectors, we take the union, we get a hyperplane arrangement. Now I know not everybody's familiar with Weyl groups, so let me say that the typical example of a Weyl group is just a symmetric group. So rank n means we have to bump up the number of the size of the permutations by 1, so we have Sn plus 1. Okay. If we think about what the reflections in the symmetric group are, with its typical representation, it's just transpositions from I to j. So the transposition has 1 minus 1 eigenvalue, and that's the vector ei minus ej, where the ei is a standard basis vector. And then its kernel is the hyperplane hij, which is the hyperplane which has the I and j coordinates equal. Okay, so the braid arrangement, in this case we call this root arrangement the braid arrangement, is the union of those hyperplanes. And then the total root system, I didn't mention that, but we just take the negatives of all the positive roots. Okay, so associated to a Weyl group, there's some combinatorial data we call the exponents. It's just a list of integers, and they're very important in the theory of Weyl groups because they appear all over the place. One place they appear, we can define the Poincare polynomial of the Weyl group. So we just sum over all the elements of the Weyl group. We can generate in series weighted by the length of the elements. And it's a classical theorem that this Poincare polynomial factors into a product of q integers. So here by a q integer, I just mean 1 plus q squared all the way up to, in this case, q to the mi. Okay? So the Poincare polynomial factors in this form. I should also mention this Poincare polynomial, if we double the degrees, this is the Poincare polynomial for the cohomology of the full flag variety. And so these exponents give us the Betty numbers of this flag variety. Here's another place the exponents show up. So we can take our root arrangement, type A, that's just this braid arrangement. We think about it as a complex hyperplane arrangement. We take the hyperplane complement. And we can look at the Poincare series for the cohomology of this complement. And we just get a polynomial. So I use Q for the Schubert variety side and T for the hyperplane arrangement side here. Okay. So this is cohomology. We've heard a lot of things about this being in the stratosphere already. But in this case, this is actually a very combinatorial object. It has a presentation as the Orlick-Solomon algebra. And we can also calculate this polynomial very easily by looking at NBC sets, sets containing no broken circuit. We think about the matroid corresponding to this root system. We can also have a combinatorial version of this polynomial in terms of the group. So if we change our length function to the reflection length, or the absolute length, so it's the minimum number of reflections we need to get an element. The length would be the minimum number of simple reflections, or for the symmetric group, simple transpositions we need to get. So if we change from L to L prime, then we get this polynomial Q. And it turns out that this polynomial also factors, not as the product of Q integers, but just linear factors with the exponents times T. And I want to point out while we have both of these on the same slide, if we plug in Q equals 1, of course we just get the number 1 plus mi. And we plug in t equals 1, we get the number 1 plus mi. So these two polynomials agree when we plug in q equals 1 and t equals 1. Oh, so I should say really quickly, fortunately time is limited, so I can't say all the different places things appear, but there's a very quick way to calculate the exponents from the root system called the constant rule, or Kosten-McDonald-Shapiro-Steinberg rule. And if we do this for Sn plus 1, the numbers we get are just the numbers 1 up to n. Okay? So the exponents for Sn plus 1 is 1 up to n, but in general they can be a little more complicated. Now, I'm going to talk about Schubert varieties. So we've got a flag variety, and this variety is stratified by Schubert varieties. And the important part about this, I'm not going to talk anything about the geometry of these things, except to say that there's one for each element of our Weil group. So in other words, for our symmetric group, every permutation gives us a Schubert variety. And we also have on our Weil group Brouhat order, and this is closely connected to Schubert varieties. We could actually define it by saying that U is less than or equal to V in Brouhat order if and only if the Schubert variety for U is contained in the Schubert variety for V. We can make a Poincare polynomial for this Schubert variety. So in this case, we're going to take, we've got a Brouhat order, we can make a Brouhat interval, all the things between the identity and the element W, in Brouhat order. And instead of summing over all the elements of the group, we just sum over all the elements of the interval. And what we get is a Poincare polynomial. If we double degrees in this, we'll get the Poincare polynomial for the cohomology of the Schubert variety instead of the full flag variety. And so Schubert varieties, very important set of varieties. So natural to ask geometric questions about these varieties, like when is this variety smooth? This is a question with a long history. Some of the people in this room, I think, have been involved in this. And it turns out, for combinatorics, it's a lot easier to talk about an approximation to smoothness and ask the question, when is a variety rationally smooth? So every smooth variety is rationally smooth, and for Schubert varieties, the converse is, maybe it's a little too strong to say almost true, but it's mostly true. There are a few exceptions, but in the simply laced cases, every rationally smooth Schubert variety is smooth. And the reason this is much nicer to think about is we have this Carroll-Peterson theorem, which says that the Schubert variety is rationally smooth if and only if the Poincare polynomial for this Brouhat interval is palindromic, which means if I read the coefficients off from bottom degree to top degree, it's the same, I get the same list as if I read from top degree to bottom degree. So, in other words, if we think about this Brouhat interval as a ranked coset, what we're saying is that the Schubert variety is rationally smooth if and only if this ranked coset is ranked symmetric. Now, before I go into that, I should say this whole picture applies very generally, not just for Weil groups, but for any kind of Katz-Moody Weil group. But for finite Weil groups, there's a very deep theorem. Notice I've dropped the Schubert varieties now. I'm just talking about W, so that could be a permutation or an element of a Weil group. Since we're just talking about properties of Brouhat order, we really can talk about the elements being rationally smooth. So for finite Weil groups, the theorem says that W is rationally smooth if and only if the Poincare polynomial factors into a product of Q integers. So if we think about a Q integer, 1 plus Q up to some power of Q, that's a palindromic polynomial, and we multiply palindromic polynomials together, we get something that's palindromic. So it's clear that if the Poincare polynomial factors like this, then we have a rationally smooth Schubert variety. But the converse is much harder to prove. Gasharov proved it for type A, and around the same time, Billy proved all classical types. And some of the cases in type E remained open until recent results of Achilles-Carroll that approach this from a geometric perspective. Here's an example. So we haven't really seen any examples so far. So S2 is just a simple transposition to exchanging 2 and 3. Same with S1, exchanges 1 and 2, and so on. So if we take this reduced word in S6, has length 11, we can calculate the Poincare polynomial of this thing, the Brouhat interval. So it's a degree 11 polynomial, but if we look at the coefficients, it's palindromic. So if I start reading from the bottom, 1, 5, 14. If I start reading from the top, 1, 5, 14, we get the same thing in both cases. So this is a rationally smooth element. And if we factor it, we see it factors as the Q integer 2, and then the Q integer 3 squared, and then 4 squared. So our exponents in this case, we have to subtract 1 1, 2, 2, and 3, 3. Okay, so far, what we see is that we've got this picture of exponents for Weyl groups, and these exponents show up all over the place, and I've only mentioned two places they show up. They show up in the inversion, the root arrangement, and they show up in the Poincare polynomial. And then we see that for rationally smooth elements W, we actually can define exponents by just looking at these factors of the Poincare polynomial. So it's natural to ask, does this picture extend? If these are really exponents of the Schubert variety, then they should behave like exponents. They should show up in other places. In particular, there's a nice way we can associate a hyperplane arrangement to any element, and we should expect the exponents to show up here. So we can define the inversion set of an element. We just look at all positive roots, which are sent to negative roots by W inverse. And the inversion arrangement is just all the hyperplanes perpendicular to the inversions. The size of the inversion set is the length of the element. Okay, so the inversion arrangement is a hyperplane arrangement with LW hyperplanes. The name is probably pretty familiar. For Sn plus 1, we have an inversion would just be a pair ij, I less than j, and wi greater than wj. And now when I say inversion, I really want to think about not the pair ij, but the vector ei minus ej. So for type A, we have a permutation. We just write down all vectors corresponding to inversions and take the hyperplane arrangement for that. And we can, given any arrangement, we can look at the cohomology of the complement. It's going to be really handy to have this. When I plug in t equals 1, you get the number of chambers of the arrangement. If we think of it as a real arrangement. Now, what we'd expect is this inversion arrangement for a rationally smooth element to factor into linear factors with the exponent showing up. If we want to see that happen, we need some explanation for why this polynomial is going to factor. So for the root arrangements, such an explanation is provided by the notion of freeness. Now there's a talk tomorrow on freeness of hyperplane arrangements, and it's actually, I'm hoping I'll have time to say something about connections with that talk. So I'm just going to say there's a certain module of derivations we associate to the arrangement, and the arrangement is free if this module is free. Now, famous theorem of Terrell, if we have a free arrangement, then the Poincare polynomial factors. It so happens that all root arrangements are free, so that provides an explanation for why in the kind of the classical case where we have the whole root arrangement, we get the factoring of this Poincare polynomial. And these, the numbers that we show up here, they have a nice explanation in terms of this module. They're the degrees of homogeneous generators. And so I'm going to call these co-exponents of A. Okay, so now let's look at what happens with inversion arrangements. So there's some reason to think that this whole picture should go over to inversion arrangements. In particular, when we have the symmetric group, theorem of O, Postnikov, and U says we have a rationally smooth element, then the inversion arrangement is free, and the co-exponents of this free arrangement agree with the exponents of W. Now their result isn't quite stated like this, but it's pretty simple to get this theorem from what they did. In the case that we have the whole root arrangement, this Poincare polynomial also had a nice combinatorial interpretation in terms of the group, with the absolute length, or reflection length. And this polynomial was studied in type A by Hellman, Linnaeus, Teresian, and Slofstra, and in all finite types by Hellman. And they proved that if the number of chambers of the arrangement, so remember that's just this polynomial evaluated at 1, is equal to the size of the Brouhat interval, then a similar interpretation holds for this polynomial group. And in particular, Hellman shows that if we have a rationally smooth element, then the number of chambers is equal to the size of the Brouhat interval. So for rationally smooth stuff, we also know this Poincare polynomial of the arrangement is well behaved. Okay, so this is probably hard to see, but it'll be on the top of the next slide. So what we'd like to see is that in all types, the inversion arrangement is free for rationally smooth elements, and the co-exponents agreeing with the exponents. Surprisingly, something stronger happens. Okay, so that is true, but it comes very close to characterizing when the element is rationally smooth. So it says at the bottom here, actually I'll just go to the next slide. Okay, so here it is the same thing at the top. If we have any Weyl group, so this is a finite type Weyl group, an element is rationally smooth if and only if the inversion arrangement is free. And then, so we're very close to just having a hyperplane characterization of rationally smoothness here. And then we've got the number of chambers. We need one piece of data from the Bruhat interval side. We need to know the number of elements in the Bruhat interval. So we don't need to know actually anything about the relations. But if the number of chambers is equal to the size of the Bruhat interval, then we just need to check freeness, and that'll apply rational smoothness. And of course, if this condition is satisfied, then our exponents, defined in terms of the Poincare polynomial of the Bruhat order, are equal to the co-exponents of this hyperplane. Here's the example, the element we had before. It was a length 11 element. So this is an arrangement with 11 hyperplanes, and we calculate our Q polynomial. We'll see it factors. Our exponents were 1, and then 2 with multiplicity 2, so we have 1 plus 2t squared. And then 3 with multiplicity 2, so we have 1 plus 3t squared. I want to talk about some aspects of the proof of this theorem here. So maybe I'll skip through some of this, not to take too much time. But I'll say that, so the easier direction is actually to prove that if the inversion arrangement is free and the number of chambers is equal to the size of the Bruhat interval, then the Schubert variety is rationally smooth. And the reason it's easier is because we can use some heavy machinery. This pattern avoidance criteria for rational smoothness due to Billy-Postnikov that holds in all types. It's useful still to think about the type A case. So here there's this Slofstra-Sanjay theorem that says that permutation is rationally smooth, actually smooth. They're the same thing for the symmetric group. If and only if the permutation avoids the patterns 3, 4, 1, 2 and 4, 2, 3, 1. And it's not so hard to show that the arrangement is free if and only if the permutation avoids 3, 4, 1, 2. And then a result of the paper mentioned previously says that the number of chambers is equal to the size of the Bruhat interval if and only if W avoids 4, 2, 3, 1, plus another 3 permutations, which are longer, but you can check that those permutations all contain 3, 4, 1, 2. So if we put these two conditions together, then we get the set of permutations that avoid 3, 4, 1, 2 and 4, 2, 3, 1. Now, the harder direction is to show that rational smoothness implies inductive freeness. So inductive, that word's there, I haven't mentioned that before, but that's there for the experts. Okay? So rational smoothness implies freeness. In the type A case, this turns out actually to be a lot easier. So type A is the symmetric group. So there, the root arrangement is a graphic arrangement. Any sub-arrangement of the root arrangement is a graphic arrangement. And there's a very nice characterization of when a graphic arrangement is free. I believe it's originally due to Stanley, and it says that the graph has to be coiled. So what we can do is we can use that property to analyze, to show that the arrangement is free. In the other types, I'm not aware, at least, of any similar results. So we have to look for different methods to actually prove that the arrangements we get are free. And so what we do is we use this theorem. So if we have a parabolic decomposition, so here J is a subset of the simple generators, and we're looking at the subgroup generated by that. And U is an element of that subgroup, and V is a minimal length coset representative. We can factor any element like this. So the theorem says that this parabolic factorization is a Billy-Postnikov decomposition. I'm not going to say what that is, except to say it involves Bruhat order. And it's a tool that's proven very useful for studying rationally smooth Schubert varieties in recent years. So W equals UV is a Billy-Postnikov decomposition, and this relative Poincare polynomial is a Q integer, if and only if when we take the flat corresponding to all inversions coming from the U portion, we get a modular co-atom of the inversion arrangement. Okay, so in other words, what we've done is we've related something about Bruhat order. Both of these conditions involve Bruhat order, Billy-Poslikov decomposition, and the point-array polynomial. We've shown that's equivalent to basically a linear condition, that this flat is a modular coatom of the arrangement. So there's a sequence of work, mainly by Billy, also Billy-Poslikov, and then a very nice summary by O&U, a paper actually at FPSAC that kind of inspired this proof. So it says that every rationally smooth element, if we have a rationally smooth element, then it has a Billy-Poslikov decomposition like this. So in other words, with the relative polynomial being a Q integer, except for, well, here are the exceptions, maximal elements in type D, E, and F, and then there are 6 exceptional elements in type E. And so we want to prove our theorem that says that if we have a rationally smooth element, we have a free inversion arrangement. Well, almost all of these are going to have a decomposition like this, so we're going to get a modular coatom of our inversion arrangement. So that's a very strong condition. In particular, it means that we can reduce checking whether or not I of W is free to checking whether I of U is free. So then we can kind of recurse down. U will also be rationally smooth in this parabolic decomposition. We keep applying this until we end up in one of these exceptional cases. If we end up in this exceptional case, well, the maximal elements, that corresponds to, so the inversion arrangements of the maximal elements just correspond to the root arrangements that we saw on the very first slide. So it's kind of a classical theorem that those arrangements are free. That leaves these 6 exceptional elements. I don't know how to prove these are free by hand, but we've got 6 elements, so that sounds like a good task for a computer. There's only one problem with that. The largest arrangement has 75 hyperplanes. So the naive algorithm for calculating whether something's inductively free with an arrangement of 75 hyperplanes takes a very, very long time. What we can do is use a standard trick here of trading CPU time for memory. So with a lot of optimization, so memoization, if you know what this is, and making sure we can pack everything in as tightly as possible, we managed to verify the inductive freeness of this thing in only 30 minutes, but it used 26 gigs of RAM. We're very fortunate in the Davis Math Department to have a computer with 60 gigs of RAM, so this was no problem. A friend of mine pointed out to me that 10 years ago I probably would have had to say this theorem was true except for these 6 exceptions. It would have been a lot harder for me to get access to a computer with so much memory. But nowadays, fortunately, memory is pretty cheap, and this is not a big deal. Of course, with a complicated computer program, we always have the question, is this correct, the result we get out of this? So what we can do in this case, and I learned this, it's a standard technique to generate a certificate that verifies the correctness of a result. I learned this for inductive freeness from a paper of Barakat and Kuntz. In this case, the certificate is only 50 megabytes, let's say that. So hard to verify by hand, but a much simpler program can verify the certificate. Okay, so that's all I'm going to say about the proof of that theorem. I want to mention a connection with this talk tomorrow. So inversion arrangements typically aren't free. There's another nice class of subarrangements of a root system that are free. So if we have an ideal subarrangement, then that arrangement is always free. And I mentioned this McDonald, Steinberg, Shapiro constant rule. I think that's a different order now, but I'm not sure what the order should be anyway. I mentioned that before because it's a very easy rule to calculate these exponents. And it turns out for these ideal arrangements, not only are they free, but we can calculate the co-exponents using this rule. So, so for technical reasons, I've stated this for simply laced groups here. So if we have any element, it doesn't have to be rationally smooth, such that the inversion arrangement is free, there's a procedure we can do on this arrangement called Peterson translation, and we can translate it to an ideal subarrangement, which will definitely be free. And these two arrangements will have the same co-exponents. So what we actually get is that when this inversion arrangement is free, there's an analog of the constant normal, as long as we do Peterson translation first to make it into an ideal subarrangement to calculate the co-exponents of the arrangement. And for experts, I'll say this proof uses a recent result of Abe and Yoshinoda to reduce basically just to type A3. I have an example. I've got, I think, 1 minute left. This is the last slide. That's good. An example of this Peterson translation. Maybe I'll put this on the board because it's a little easier to visualize. So here's the root system in type A. These alpha i's are the simple roots. So in terms of what I had before for the symmetric group, this would be EI minus, or this would be E2 minus E3. Okay, and I have an element there, an inversion set, which is actually not rationally smooth. And I'll circle the ones that are in the set. So it's everything except this alpha 2. And then what we do is we translate by an element of the set. So in this case, I'm going to translate by alpha 1 there. I've got tau IW alpha 1. So I'm going to translate by this. And what I do is I look at the alpha 1 strings. So what that means is everything that differs by just adding or subtracting alpha 1. So here's an alpha 1 string, these two elements. And here's an alpha 1 string. And this is actually an alpha 1 string of just one element. Okay? And what I do is I compress along the alpha 1 strings. So every time I have a lower element that's not circled, I just move stuff down. So here, both elements are circled, I don't do anything. But here the lower element's not circled, so the translate by alpha 1 is going to be alpha 1, alpha 2 plus alpha 3, 1 plus alpha 2 plus alpha 3, and alpha 3. So this is definitely not an ideal. So an ideal in this case is an ideal in the root post set with dominance order. And it means we need to have, if we have something like this, we need to have everything below it. This is one step closer to an ideal. We've put in alpha, we've taken out this alpha 1 plus alpha 2, and we put in alpha 2. Still not an ideal because we've got this element in our set and this element appears below it here. So we do one more translation step by alpha 3, and when we do, so we're going to translate by this element will move down, and we'll get an ideal, and we can calculate the exponents. So what we do is we just calculate the, so let's see, so the exponents are 1 and 2. So we take the number of things of height 1 and subtract the number of things of height 2. And that's the multiplicity of 1 as a root. And then I take the number of things of height 2, subtract the number of things of height 3. And that's the multiplicity of 2 as a root. So here we've got 2 things of height 2 and 0 things of height 3. We get 2 with multiplicity 2. Okay, so that's the end.
What's your certificate exactly? Is it like an explicit factorization or something?
So the certificate in this case is for inductive freeness. So inductive freeness means we have one hyperplane we can throw away and still get a free arrangement. And then we also restrict and we get a free arrangement. And then the exponents agree in some way. So basically it's a list of which hyperplane you should restrict and throw away. Yeah. And then for each of the restrictions, a certificate, and the one we throw away is.
Any other questions? Thank you again.